This is the Smart Parking System, Group B. Here's an overview that showcases how we have envisioned the Smart Parking System to work. Number one, the camera detects a car entering a row in the parking garage. Number two, the camera sends a data package to the database, and the data package contains the camera ID and the change in spaces, which in this case is a -1. Number three, the Java program in the server is constantly checking for updates in the database. Number four, once the server finds the new data, it calculates the new available spaces in that row of the parking garage. Number five, the server updates the PCB by sending a data package using the IP address of the PCB. The data package contains the new number of available spaces. Number six, the PCB receives the updated number and updates the LED sign with that new number. In the case where a vehicle is leaving a parking garage or leaving a parking row, the camera will send a positive number instead of a negative number. A positive number means that one more parking space is now available. Now the rest of the process is the same.
So here we have pictures of the top and the bottom of our PCB. Referring to the top picture, on the left half of the board, we have the Ethernet port, a DC power jack connector, a 3.3 volt linear regulator, as well as a couple of test points to measure the voltage before and after it has been regulated. These test points could also supply power to the board via an external source if need be. On the right side of the board, we have the PHY chip, which is the smaller of the two chips, our MCU, an oscillator, an 8-pin female header used to connect to the debugger, and a 16-pin male header, which is used to communicate with the LED sign. Now going to the bottom of the board, I did decide to include some of the SMD components here, as it would allow us to get bypass capacitors as close as possible to their respective pins and make for a more compact design. However, I would like to mention that because I did decide to design the PCB this way, it gave some challenges with the solder mask that came with the PCB. So in this video, the LED sign is being driven by the PCB and powered by a DC power supply available in the lab. The PCB is connected to the host computer via a debugger and is being powered by a DC jack connected to an AC outlet. The point of this video is to show that we can access all the LEDs and change the colors of them. However, when a program is loaded to the PCB, there's sometimes a delay where the LED creates some random colors and then gives us the results we were expecting. Additionally, the last column on one of the signs sometimes creates a color that we're not expecting. And these are issues that we are still trying to find a solution to as of now.
Our LED display has been making good progress so far. We've been able to change what kind of colors are shown. And we're able to do things like as shown here, where we have two different colors displayed at the same time. And as shown, these two colors are able to be pushed to both displays at the same time. However, there have been some difficulties with the display, as just there's not very much documentation available on the internet at the moment. The display has its own documentation is about 2 pages long with just technical specs about electrical characteristics. However, what we do know about the display is there's 384 bits that can be shifted into its 24 LED controllers every time. And those 384 bits are then latched. And after every latch, you have 16 lines. You have 16 different lines that need to be displayed at once. So it's a 1 in 16 scan rate. By having this system, we can basically push out the 384 bits 16 times, and it'll flash between those 16 different configurations, which then illuminates the entire screen. And this allows us to control every aspect of the display. At the moment, though, we have not figured out how to get specific shapes that we want drawn. I'm able to control any line, any row that we want to display, but at the moment we haven't figured out specifically how to get shapes, but we are on the way to figuring that part out. Ethernet hardware is in place at the moment. We don't have anything else left to do with that. We have our PHY chip, we have our oscillator. It should be fully functional. The only thing left is to get it programmed and working properly. How the board is going to be powered is also via the Ethernet, power over Ethernet. So we have a splitter which is going to split out power to our barrel jack and power the board, in addition to allowing Ethernet communication with the server. This shouldn't be too hard to implement, especially in comparison to the LED driver, since Ethernet is already a very standard protocol and there's a lot of information currently available.
The database is located in the server, and it is created using this program, MySQL Workbench. The database engine is already installed in the server, and we can connect to it by clicking here. The database is then created using a script. A script, it's nothing more than a set of instructions to create all the tables we need. In addition to creating all these tables, it populates the database with sample data. We are using sample data because, as of now, the camera nor the custom PCB and the LED signs communicate with the server. Now let's run the script. Now here are all the tables created. Let's take a look at camera log table. For example, in row 1, we can see that camera with ID 1 log a -1. That means that a car was detected entering a parking row. Now the number 1 in this column means that this row is a new data row, so it needs to be processed by the system. Let's talk about the server now. Initially we had to choose a Raspberry Pi as our server because the Odyssey was on back order. However, we started having issues with our Java program running on the Raspberry Pi, running our database, and overall configuring the Raspberry Pi. Therefore, we switched to this mini PC that has an Intel processor and where our Java program and database run smoothly. In addition to hosting the database, the server also runs the Java programs. Our parking system has 2 programs. The background service, which is the program that is doing all the heavy lifting of checking for new updates from the camera, calculating the changes on the number of spaces, and updating the LED displays. The second program is the user interface, or GUI, which is used to monitor the parking garage system and make changes to the system like adding a camera or adding a new LED sign. Let's see how the background service program works first. Now remember that this program is always checking the database for new data. If we go back to the database, we can see that all these rows are new because it has a 1 in this column. Now this program also attempts to update the LED signs, but since there is no communication now with the LED sign yet, I created another program that behaves as if it were some of the LED signs. So currently LED display says here that it's listening and is waiting for updates from the control unit. Now if we run the program, it will communicate, load the information from the database, and you can see how this program behaved as the LED. You can see that the control unit was connected and update receive, and then updated. It printed 97 and then 96. It's printing twice 96 because it's updating 2 LED signs that belong to the same section. Like a parking row can have 2 ways to get into that row. So we planning on having like LED signs on each end. So that's why it needs to update 2 LEDs on that row. It goes down to 95. And also if we check the database, we refresh here, we can see that all this data has been processed because now there is a 0, meaning that these rows are not new anymore. And if we go back to the program, you can see here that the parking system is waiting for new updates. Now let's talk about the graphic user interface. We can run it here. This information in the background is just printing information that we're using for development purposes. But the graphic user interface is this one right here. The first thing you can see is that on the corner, the parking system online, it says that it's online. So the GUI is monitoring this program. And since this program is actually waiting for new updates, it is saying, the GUI is saying that it is running. If I were to close this and stop it, you will see the parking system goes offline and it tells us there is something wrong. And if I run it again, it should turn green. Okay, so now we are in the garage overview of the graphic user interface. It displays the current information on the entire parking garage. We can see currently there is 1% full. Although it says 2% full here, this is 2% off level 1. But when we calculate the entire parking garage, it's of course 1%. I can click refresh and you can see on the background how this updates. But since there is no camera updating anything right now, there is nothing going on, nothing to update on this. If we go to live view, we will have also the latest updates from cameras. We could refresh as well. We have this to select a camera in the future where you can connect to a camera and see a live video feed of what's going on. There is nothing on this sections. These are to be developed. We have a button here that we can test the database connection just to troubleshoot purposes. We can display the address of the database or where we are connecting. There is an about page, and that's the graphic user interface.
A pre-trained machine learning model is being used for the vehicle detection functionalities of our project. We've had to further edit the model to accommodate our project needs, like the count object function. Also, we'll need to add the functionality of emitting the count value and update it in the database. Now, here is an ongoing vehicle detection and count demonstration video. In these first 8 seconds, as you can see, the camera can detect a car right in front of it, as well as a vehicle across the driveway. It also demonstrates the capabilities of detecting moving vehicles. In this particular frame, we can see 2 vehicles and the camera is being able to detect them both despite of the distance. However, trying to move the camera around, as it can be seen, poses the problem of inaccuracy. However, once the camera is stabilized, the correct vehicle detection functionality reinitializes, as it can be seen here. Both the vehicles are being detected, and on the left-hand side of this, you can see the count functionality we have added, where it displays the object counting in this current frame, which is 2 cars, and you can see the vehicle count is 2.
All right, for specification number 1, we have our LED display. The display, we want to hit a minimum brightness of 1000 nits. Our display is rated for 1000 nits. However, we could boost it to even higher just by cranking up the amperage for our display. We want a comfortable visibility of the text. So in order to achieve that, we want to be able to see it from a good distance. And around 50 feet is seen as a pretty good distance within these covered garages that we're in. We're going off a rule of thumb of for every vertical inch of text, we have about 10 feet of visibility. So when you multiply that by our display being 5 inches vertically, that gives us 50 feet of about comfortable viewing distance from there.
Some of the core engineering specifications on the computer vision part of the project was that the camera would detect vehicles accurately, and the camera would implement power over Ethernet concept. Or in other words, for the camera to function properly, it would only need to be powered by the Ethernet switch. Now here is a demonstration. In this video, you can see the camera is disconnected. And now we'll connect the camera with the Ethernet cable, which is connected with the switch in the video. And once the cable is connected, as you can see, the camera boots up with the green flashing light, which refers to active connection according to the data sheet. Now for accuracy, and previously we have seen the camera was able to successfully detect 2 cars with almost 100% accuracy. However, the only complication was due to the movement of the camera itself. But in our project, the camera is planned to be mounted on a tripod. Thus, the restriction would not apply with the more stable system. Now, in our next video, we've tried to show multiple cars being detected accurately. As you can see at the beginning of the video, there are 5 vehicles available, and once the camera was stabilized, all 5 of the cars were detected. And at the end of the video, after stabilization, the camera was successfully able to detect one car at a distance across the driveway accurately.
Another specification we had was about having a user-friendly interface. In the demo, it was clear that this GUI is simple and clear to use. We used a good contrast between dark and light and yellow colors to help differentiate distinct parts of the GUI.